Yeah, welcome to this course on Illumination Engineering and Electric Utility Services. Continuing with the previous lesson, we go on to the next lesson. What are incandescent lamps? State the components of an incandescent lamp. Understand need for inert gas in an incandescent lamp. What is lamp darkening? State factors responsible for performance of an incandescent lamp. If we look back till now, we have established the need for artificial illumination, which has enabled us to extend all our activities round the clock, round the year. And in doing this, we have used artificial sources of light, and sources of light have evolved, say, from oil lamps, wax candles, vapor lamps to electric lamps. So, this has been the thing, and today needless to emphasize that most of artificial illumination is in the form of using some form of a electric lamp. And one of the predecessors of these electric lamps has been the incandescent lamp, and that is the title of this lecture. Incandescent lamps have been there right from very beginning. In fact, we had seen that all our artificial sources are aimed at creating atmosphere close to natural illumination. Remember that the most important source of light and energy in nature has been sun, and to some extent moon in the form of a reflected energy from sun. So, the looking back at the parameters of natural light, we have sun, which is about 93 million miles away, having a diameter of 865,000 miles, with the temperatures rising much greater than 6000 degrees centigrade, give rise, or you can be said to be having a luminous intensity which is 2.3 into 10 power 27 candela, which is, remember, in the last class we had, earlier class we had standardized what is a standard unit of luminous intensity, which is originated from original wax candle, and primary standard established based on this was using a good radiator maintained at the freezing or melting temperature of platinum. The next most important natural light is been the moon, which actually reflects the sunlight, is around 240,000 miles away from the surface of earth, having a diameter of about 2160 miles. Its luminosity can be estimated to be 1 into 10 power 17 candela. Now, we are looking at the application of artificial sources to achieve similar light conditions in all our activities to be able to function. In doing this, we said we may be employing one of the physical properties, and the 4 physical properties that are often employed have been detailed in one of the earlier lectures is incandescence, luminescence, fluorescence and phosphorescence. Remember that incandescence is nothing but thermoluminescence, working on the principle of a material being maintained at a higher temperature, which gives rise to radiation. In this respect, we saw the radiation ability can be explained by the Wien's law, which says that the radiation is proportional to the 4th power of temperature. That has to be borne in mind. So, the lamps employing these are called incandescent lamps. Common naked lamps which we have been using all along or commonly used fall under the category of incandescent lamps, and in the sense of a measurement or analysis, one could view these lamps as point sources of light. In fact, incandescent lamp has been invented by Thomas Edison in the year 1879. This employed essentially a carbonized paper as a filament, and carbon which was drawn in the form of a filament was very fragile and could not be kept sustained for a longer time, and to have stability it was in fact coated with a hydrocarbon to improve its properties. It was probably in the year 1893 that cellulose filament was developed, and this was developed by dissolving an absorbent cotton in zinc chloride. So, this is the process through which the lamp went through. As the name implies, it calls for having an element maintained at a high temperature. On the passage of electricity, it develops a heat and gets raised to higher temperature, and it radiates. Now, to be able to use over the expected life of the lamp, we expect it to be stable without any damage to itself and be able to produce the required light. And one had to go through a series of changes before it was. Now, this filament is mounted in vacuum, and typically this filament had a light output of the order of 3.3 lumens per watt. Recall the light flux we mentioned is talked in terms of the lumens. We did say, supposing we have a point source, the light output radiated over a steradian is what is the light flux due to one source. If the source is of one candela and subtends an area of 1 meter square, that is what is 1 lumen. Now, since the lamps employ electrical energy, which consumption of electrical energy is often mentioned in terms of power or watts, the efficacy of a lamp is talked of in terms of the lumens per watt, that is, how much of energy is consumed in giving effective light output or light flux. So, if we look back, Edison's lamp or carbonized filament lamp, which of course went through stages of improvement by way of employing hydrocarbon coating and dissolving cellulose filament in the zinc chloride solution, could radiate at most about 3.3 lumens per watt, and to have the stability of the filament, it was enclosed in a glass envelope. This is what we call as bulb, okay, and it was evacuated so that there is no effects of the atmosphere, and therefore, and in the lighting terminology, these lamps which were maintaining filament in vacuum were called type B. Later on, we will see there are some requirements that necessitate that this environment is not in vacuum, but it consists of certain gas, and they are called gas lamps and not the discharge lamp. Discharge lamps are different from gas lamps in the sense these are still incandescent lamps having a gaseous envelope, whereas the discharge lamps are one which actually have a arc discharge at the time of a passage of current. So, this led to improvements in the filament. Filament is the heart of the lamp, and the efficacy was to be developed, and that is how there have been improvements. In the year 1905, the metallizing was done, and it could be improved, say, from 3.5 lumens per watt to about 4 lumens per watt. At the same time, in the European continent, things were being tried out with other materials like osmium. There again, no doubt, it gave a good light output. Efficacy was much better than what it was with the carbon filament lamp. it gave about 5 lumens per watt, but the fragility was still high and it was rare and expensive. In fact, this led to looking for materials which could be ductile and which could be drawn in the form of wires and at the same time be able to give good light output. So, the efforts were on to increase from the 3.5 lumens per watt to higher and higher levels, and it was tantalum was found which was quite ductile, but would crystallize an application of AC. Today we remember, although there are two kinds of electric power supplies possible, DC and AC, most of our utilization is in the form of AC, for the simple reason AC enables us to step up or step down the voltages quite conveniently, and the wonderful device that enables us is the power transformer. The other thing is, most applications require some kind of a motion, and the induction motors have been the versatile motors. Now, all this led to a better materials, and it was probably in the year 1907 that the tungsten filaments entered the scene with initial light flux efficacy of 7 lumens per watt. This was obtained by taking finely divided tungsten wire or tungsten powder, which is mixed with a binder and squirted through a die, giving rise to a thin conductor. And in the year 1911, it was Coolidge who could produce tungsten in ductile form. So, you had amorphous tungsten which was mixed with a binder and squirted through a die to draw the filament, whereas Coolidge developed the method to get ductile tungsten. In fact, even today the incandescent lamps are employing tungsten. The understanding of incandescent lamps becomes very important because, be it incandescence, electroluminescence or fluorescence, all of them need some form of a initial incandescence to be there. We will come to know when we look at the discharge lamps that the arc discharge is between two filaments, which again are tungsten filaments. So, this enabled getting a continuous uniform filament which is rugged and very high efficiency. And Langmuir found that with the insertion of inert gases, in fact he developed the properties of inert gases, the radiation efficiency could be improved considerably, and possibly in the year 1913 the type C lamps or the gas lamps entered. So, we have the filament as the heart of the lamp. It has gone through a lot of changes from the days of Edison. We started with carbon, and all the time the search was for being able to draw a fine continuous filament of uniform cross section. That is what enables good ability. In fact, when you talk of a lamp, you talk in terms of getting nominal light output at the nominal rated voltage. This shows the picture of a lamp. All its components are shown. You have here shown the outer envelope, which is often made of glass. It is called bulb. It is transparent in its initial thing. In fact, these days you have the various types of glasses employed. One is, if you have the completely opaque glasses like coated white, gives rise to diffusion, because we talked about the effect of light radiation falling in the line of vision would create glare, and that will be disabled. And this glass envelope is what we refer as bulb. Now, the green thing that's shown as basically it's shown as a drawn wire placed there is the tungsten filament. As we go along, we will find that this at lower watts it could be a wire spread out in that form, but at higher wattage levels, you will find it is in the form of a coil or a coiled coil. That means a coil is recoiled and placed across the two leads. Lead-in wires which are made of nickel. In fact, when a bulb fuses, it is this filament that fuses because of the excess current. There are filament supports which are made of tungsten or molybdenum. The glass envelope is there, and you have the two base contacts through which electricity flows into the bulb. That is the basic structure of a bulb. Now, this envelope in the early stages was completely evacuated. These base contacts are invariably made of tin and the base cap is also made of aluminum. So, these are some of the issues. Now, the tungsten is known to have a specific gravity of 18.81 before drawing, which improves after drawing to 19.3 to 20.2. Incidentally, tungsten has a higher melting point of the order of 3655 degree Kelvin. It is a very important issue. Remember that in the phenomena of incandescence, the temperature at which it is maintained is very important, and we have seen that the radiation output is proportional to the fourth power of temperature. We have seen that tantalum and osmium were also experimented in the process of development of filaments, and they have temperatures of the order of 2972 degree Kelvin and 3172 degree Kelvin. By sheer virtue of having a higher melting point, we are in a position to get higher output from the tungsten filament. Theoretically, the tungsten filament could give up to about 52 lumens per watt at the melting point, and it may be observed or it may be seen practically highest of the order of 36 lumens approximately per watt has been achieved. You have on the high end 250 watt floodlights which have a life of about 3 hours. You could be having that is the lowest life, and you do have normal 40 watt lamps which have a life of about 1000 hours. If you look at the data given here, we have a 1500 watt 115 volt lamp, 115 volts mind you, 1000 hour life with 22 lumens per watt, whereas a 6 watt 115 volt lamp has a higher life of about 1500 hours with a output of 6 lumens per watt. The issues are twofold. In fact, if you see this, even at such low wattage, we are having better than what it was in the initial stages. Smallest lamp developed is employed in surgical instruments. In fact, this is often called grain of wheat, which consumes about 0.17 watts and delivers about 0.35 lumens. It is also called sometimes grain of rice or grain of wheat. If you go to a shop, a neighborhood shop, he may call it rice lamp, which is often used for decorative purposes. And in fact, one of the important festivals around the country where it is used is Deepavali and then the Christmas. The largest lamp developed is around 50 kilowatt power, which gives out about 1,600,000 lumens, which is equal to about 1000 units of 100 watt lamps. That is the kind of a thing. Remember that it consumes lesser power. That is the thing. Now, we had initially vacuum lamps which were called type B, and later I said the certain properties, stability properties of tungsten necessitated, because tungsten remained as the filament to be used. It was the introduction of the gases, especially Langmuir's studies showed that stability of this filament is more in the presence of gas. Now, what happens when the current passes through the filament, there is elevated temperature because of which the radiation takes place, but simultaneously there is certain vaporization of the tungsten particles from the surface. So, in the process the amount of element available or the resistant variation takes place in due course, and that would change the light output apart from the usual aging which is associated with any device. So, that being the case, it was found that once you have a gas in the thing, it will reduce this vaporization. The simple thing is that these gases which will get carried in the convection currents combine, they get ionized at a very low temperature, and they combine with these tungsten particles which are evaporated, and as they cool they come back and get deposited on the filament. So, that is the process, and so the inert gases are employed, they decrease the vaporization of the tungsten, and the most suitable gases have been found to be nitrogen and argon. It is said the losses in a gas are proportional to the velocity of gas molecules, and velocity is in turn inversely proportional to the square root of atomic weight, and these have been found considering that their atomic weights are 39.8 and 28 respectively for argon and nitrogen. That is the thing, and it is, as I told you, it is the ionization potential which is low. That is the reason why it enables a mixture of argon and nitrogen with 85-15 has been found to be very suitable. As already said, when the current flows, there is elevated temperature. At this elevated temperature, surface particles tend to vaporize, which go and get deposited by the convection currents on the lamp walls, that is the interior of the bulb, and these, because of the ionization of the inert gas present, these ions go and combine with the tungsten filaments and tungsten particles, and as a result together they get condensed, and because of the thing, as they cool, again argon releases the thing and the tungsten gets deposited. This is the issue, and that is how it helps. The other way of avoiding this particle vaporization is to have the filament confined over a small region. In fact, I mentioned at lower wattages you will have filaments spread out, but as you go to higher wattages you tend to coil them. This is the reason why we coil. It is a helical coil, and in fact if you have read the top of a bulb, you will find it is written as coiled coil. That is the reason this coiled coil is placed. In fact, this vaporization leads to deposition which we call as blackening. This blackening takes place. Here are two bulbs which we find are shown. The one is placed in such a way that the base is towards the ground, that is as though you have the light pointed towards the ceiling. You could be having a reflector placed which directs the entire lights towards the ceiling, and the reflected light comes on the object to be used. Here we can see some shaded region on top of the bulb. In fact, that is the reason where you will find there is some deposition of the tungsten. In the absence of inert gas, you will find this region gets blackened, and as a result with time the light is blocked. In a similar way, if you have a bulb mounted with the base on the top, that is you have the bulb recessed to the top of the ceiling, and the light comes directly towards the object or the table, work table, you find the deposition at the near the cap. Here it was towards the, so these arrows which are marked only on the left hand figure could not be marked because of the space shortage in the diagram. On the right hand side you find these arrows are showing the convection currents established in the presence of a inert gas which has a low ionization potential, which gets ionized and combines, gets cooled and redeposits the tungsten particles evaporated on the filament. This is the advantage. So, what do we do? To avoid blackening, we take two steps. One, we try to confine the filament to a concentrate zone by providing in the form of a coil, and coils are used, and therefore going by this we have two categories of lamps. One, vacuum lamps, which are often called type B, the other gas lamps, which are called type C. As can be seen, type B vacuum lamps are usually around less than 40 watts. All of us have seen 25 watt lamps are there, which we use in the areas which have to be lit at a lower level, but all the time. It's essentially like circulation areas. Type C gas lamps are used beyond 40 watts, and they invariably have an inert gases. The inert gas choice depends on the ionization potentials, and it's been found argon and nitrogen in a mixture of 85 to 15 is found to be suitable. As already told, during the operation of the filament evaporates and the tungsten particles deposit on the interior of the bulb. That is in the case of a vacuum lamp. Now, the tungsten filament, remember that the cross section of the filament required depends on the current, and it varies as the square of the dia. Radiation surface again varies as the diameter varies. So, these are some of the issues we have to keep in mind, because this is the thing which we look based on the operating voltage. If you are operating in, say, North America, the standard voltage levels would be around 110. If you are operating in India or Europe, it will be around 220. So, these are some of the issues to be kept in mind. This is what the lamp manufacturers keep in mind. You can see very clearly with the same wattage, decrease in voltage would call for larger cross section. Filament becomes bulkier. No doubt there is higher efficiency at lower voltages. Let us look at some of the characteristics of a incandescent lamp. Their typical curves are shown here. This is voltage versus efficiency. Needless to re-emphasize that for the light sources, efficiency is talked of in terms of the light flux per unit of electric energy consumed. That is, we talk in terms of lumens per watt. You can see the x-axis is in voltage. There are two particular voltages have been marked. One is 110, other is 220. The issue to be noted, no doubt there are two curves here, one for a 40 watt lamp, the other for a 100 watt lamp, and you have each of these lamps have a peak close to 40 to 50 volts at 17 lumens for 40 watt lamp and 19 lumens for the this thing, what you call 100 watt lamp. What else do we observe? We observe one thing, possibly for both these lamps we have somewhere around 10 lumens saturation independent of the voltage, as the voltage goes higher for a 40 watt lamp and around 12 lumens for a 100 watt lamp. That is the point to be noted. And another thing to be observed is that possibly if you take a 100 watt lamp, the variation in lumen output between 110 to 220 is marginal. It is around 15 lumens to 12 lumens. So, this is the some of the things which also will determine the life. In fact, we do use high wattage lamps to create what we call floodlights. As the name implies, it is a flood of light. Remember, floods are bulky, large amounts of water flowing. Similarly, if I create a large intensity, large light flux in a particular environment, that is the flooding of light, and these are used in sports arenas, etc., which can have a short life of about 2 hours to the typical street lights which are employed may be having 2000 hours. So, the issue one could observe, good to operate at a lower voltage. There is no doubt, if you operate at a lower voltage, you get a higher efficiency, but nevertheless the variation between the 110 volts output and 220 volt output is not so much to really warrant that kind of a thing. Remember the thing, the filament size goes on increasing as the voltage goes down. That is equally important from the designer's point of view. The performance curves which can be seen, it is is marked in terms of the change in the characteristics with rated life. If you can see very clearly the watts and amperes, I mean a good lamp, that is what we expect, is supposed to remain same throughout its life as the virgin lamp. Then the next thing which we find is the light flux and lumens per watt. You can see very clearly the lumens per watt, around 80% of the rated life itself comes down to about 90% of initial other virgin value, and around 100% life it stabilizes around 85 to 90% of the, so the change is very little. On the other hand, if you find the light flux itself, you can ensure that if I by design a design for 1000 lumens, I can expect it to give 800 lumens throughout its life. Now, the choice of the material, the design lengths and the voltage are such that its resistance is stable over the region and gives the required output. Only when it consumes the required output, you expect it to give required what you call the light efficiency. However, all of us know that the system voltage cannot be assured to be same at all times. There is bound to be necessary change in the system voltage. Here it should be mentioned that it is the current flow through the filament that is producing the radiation output, but it is the applied voltage that is necessary to produce the required current. One could see how these characteristics change with change in voltage. There are 4 curves. We have the first curve showing the lumen output, second one lumens per watt, third watts and amperes. As you can see, lumens per watt does increase, but what is not shown in this curve, as you can see, the point of intersection is corresponding to 100% rated voltage. So, only thing that is not shown is the percent life, which we will look at in the next figure. So, these are representative. As we know, increase in voltage will certainly give higher output, but there is every danger of resistance going very high, and as a result, because the temperature goes higher, current levels go higher. See, the first thing that happens is you have a fixed length of filament and applied voltage goes higher, means you are pumping in a higher current, which means I squared R, the power, the current, the no doubt the heat increases, that means temperature rise increases, therefore light output increases. Maybe light output, light efficacy also increases, power consumption increases, no doubt current increases, but there is every possibility of disintegration of the filament because of the high level of temperatures. Stability of the filament is at stake. Therefore, you have the survival curve, which is very important. As you can see, supposing I have produced about 100 lamps, and you see it is about 81% of them which survive more than 80% of the rated life, and it is less than 30% which survive at about 110%. This is a very important issue. So, if I have 100 units developed, it is only 80 units that can be really expected to give full life. In fact, this does tell us in a system what kind of a replacement schedules one has to adapt. So, there are two ways to do it. What we do at home, a lamp fuses, then we replace. Because we have few lamps, it is quite easy for us to keep track and allow it to go till the end of life. But when you think of a workshop, which is a very large workshop with large number of lamps, it may not be feasible to do hundreds of lamps. To do this every now and then, one has to really do it in a planned manner. So, this particular such data from the manufacturer enables us to have our maintenance schedules and replacement schedules. So, having known this, it is necessary for us to know on what does filament characteristics depend. Filament characteristics, when I mean the most important characteristic as far as illumination engineer goes, is the resistance, because it is the thermoluminescence that is giving us the output. So, and that depends on the length of the filament, diameter. Since the coils are involved, the coil spacing, now the kind of lead wires, kind and number of supports, method of mounting. There is no doubt number of supports and method of mounting only affect the mechanical stability, properties of gases, gas pressure, size of the bulb and shape of the bulb. No doubt in most natural systems, the spherical system is the, or spherical size, a spherical shape is the most suitable, and in fact that is why we find most bulbs have a spherical ended shape, though it may be somewhat conical at the base cap side. This is the thing. And in order to have economic service for the intended application, we try to design the filaments for uniform radiation with reasonably good accuracy of wattage and light efficiency and life rating. All are to be maintained, and that is why we saw how the survival rate comes. And in fact, I told you, if you design 100 units, it is possible to have about 80 of them to give you the required this thing. Now, all this has led researchers to look at the variation in these characteristics by the change in the lamp characteristics from the nominal ones. How do we specify a lamp? We specify in terms of two things. One is the wattage, the other is the voltage. And let us say we have a lamp rated for 100 watts, then you can, the nominal lumen output is, if it is called capital F, and the lumens per watt, the efficacy is capital E, life at this wattage or at this light output be L and volts be V. It is found that the variation in voltage with variation in wattage can be exponentially related through a relation V over V by A. In fact, we know if the assuming the resistance to be same, if the voltage reduces, wattage reduces, hence the light output reduces. Remember, one thing we saw, life may improve if you operate at a lower voltage, but light output also reduces, which means you are going to strain your eyes, which means you are going to pay higher bills to the doctor. The other alternative, in fact, the lumen output vis-a-vis voltage and the wattage is related through equation 2, which is raised to the power b and c. So, we have come across 3 exponents, exponent A relating the power consumption vis-a-vis the applied voltage, the 2 B and C relating life to the voltage and wattage. This will be very useful in the sense that once you have these exponents, depending on the operating conditions, you can arrive at the possibility of the performance of your lamp with the manufacturer's guaranteed specifications. Here the uppercase W, F, E, L, V are the nominal ratings, where the lowercase correspond to the operating conditions. Now, this shows the variation for the light efficacy is somewhat inversely proportional to the voltage and directly proportional to the life. And the last one you have is the just a moment. You have the life versus efficacy was the third equation, which is related to the life as well as lumen output and the this thing, and life with respect to the lumen output, voltage and efficacy. So, you have how many exponents? You have A, B, C, D, E, F, G, H, that is about 8 exponents. Now, let us look at some typical values. There are typical values for all these are given A, B, C, D, E, F, G, H for a typical gas lamp. What is a gas lamp? Gas lamp is a tungsten lamp with a inert gas enclosed in the envelope. What does the gas do there? It avoids vaporization of tungsten, in turn which could cause blackening of the bulb, and blackening of the bulb is totally avoided. Now, the similarly, what is a vacuum lamp? A vacuum lamp is a normal incandescent lamp. Now, what did we see? The vacuum lamps are called type B, gas lamps are called type C, and below 40 watts we have vacuum lamps, above 40 watts you have gas lamps. So, what did we observe? We observe the process of application of the phenomena of incandescent for having a artificial light source, which we call incandescent lamps, and this depends on essentially the characteristics of the filament. So, filaments, if you recall, the Edison's bulb had carbon filament which grew through several stages, and finally tungsten was found to be suitable, and this is how. And then how do we specify the characteristics? We specify the characteristics in terms of the wattage of energy consumed by this filament at a operating or a nominal voltage. We have seen that these exponents A, B, C, D, E, F, G, H essentially relate your performance of the lamp when there is a deviation from the rated voltage or rated wattage. What are the various characteristics which we are looking here? We are looking here the light flux output or the lumen, light efficacy in terms of lumens per watt, and as already said, we have the smallest lamp is the grain of wheat or grain of rice used in surgical instruments, and largest lamps could be as large as 50 kilowatt lamp, which could in principle be radiating flux corresponding to 1000 units of 100 watt lamps. Having said this, the summary of this lecture could be summarized that the incandescent is a phenomena which is thermoluminescence, is a radiation at high temperature which is being adapted in incandescent lamps, and mind you, we have other effects that are used in artificial sources like electroluminescence and fluorescence. Electroluminescence is the discharge giving rise to radiation in a gas or a vapor. It could be gas, a metallized vapor or a gas, and all these in fact are also dependent on certain filaments which are using thermoluminescence. And thermoluminescence depends on the temperature. Now, we had type B lamps which are in fact using tungsten. They have started with carbon, osmium, tantalum, and finally zeroed in on tungsten, and it is maintained in vacuum, whereas type C in inert gas, as said, the inert gas enables avoiding vaporization of the filament. The vaporization of the filament does give rise to blackening of the bulb, and this gas employed is a mixture of argon and nitrogen. What are the properties we are looking for in the gases? They should have low ionization potentials. What happens? Because of the low ionization, they get easily ionized, and the convection current set up because of the temperature. Due to the filament, they go and interact with the particles that are deposited in the interior of the bulb, and they combine. In the process, they cool and get redeposited on the filament. This is the process. Tungsten is ductile in nature and therefore is highly suitable because it enables you to draw uniform conductor of long lengths. It's got a high melting point. That's a very good thing, that over the life or over the rate of operation, it does not melt and gives rise to good light output, and hence has been zeroed in as the filament material. As already told, inert gases in incandescent lamps help in decreasing the rate of evaporation and add to the efficiency of the lamp. Higher efficiency is obtained when lamps are operated at low voltages. Yes, when you operate at a lower voltages, the life may be there. That is what we are talking about. But remember, the lower the voltage, lower is the light output. Okay, and therefore it's very, very important to know that it may not, though you get a longer life from the lamp life point of view, but efficacy of the individuals may be at stake. That's the thing to be borne in mind. So it is preferable not to reduce the voltage below 90% of the nominal rated voltage. That's the thing to be borne in mind. Filament characteristics are important, and they are dependent on the length of the filament, and we told the other technique apart from using inert gases is to coil the filament. If you coil the filament, you are concentrating over a small region. What happens if there is a coil? If there is any particle from the surface that's evaporated and trying to move away, gets redeposited on the coil, it gets confined in that space. That's what helps. The method of mounting does look at the mechanical stability. The gas employed, of course, we said normally it should be argon and nitrogen. Bulb size, naturally it depends whether it's going to create any explosion or not. Filament diameter decides the ability of carrying the current to give the required output. Lead wires, if you have a filament which can carry higher current than the lead wires, no use, because the life of the lamp is at stake. The gas pressure and shape of the bulb. Shape, as you know from the stability point of view, the best shape for all things is to have a spherical shape. Now, keeping all this in mind, we design, here it says bulbs. Bulbs means incandescent lamps are designed for uniform radiation. We would like to have uniform radiation, that is, from unit to unit you should have uniform radiation. Supposing a portion of the filament radiates much higher than the other portion, it will again create non-uniform flux output, and then it will not be productive in the sense. The accurate consumption of power, because that will enable the engineer to estimate actual requirements comfortably, and efficiency, no doubt every system should be efficient, and the life rating enables in us to decide when to replace the lamp. Maybe it's easy at home for you to replace whenever the lamp fuses. But in a large setting like industrial setting or an office setting, it becomes very important to have an idea of the life rating. What did we see? Survival rate is around, if you have 100 units built, about 80% do survive for more than 90% of the expected life. So, the questions that may be addressed from this lesson are: what are the methods employed to tackle evaporation of tungsten filament in an incandescent lamp? Why is it not feasible to operate bulbs at low voltage although it amounts to high efficiency? What properties of tungsten make it a better material to be used as a filament of a bulb? And coming back to some of the questions which have been asked in the last lesson on photometry, why can't an incandescent lamp be used as a standard lamp? Due to the aging factor, the light output of an incandescent lamp decreases with use. This is one reason why, though when shifting from wax candle, for some time incandescent lamp was thought of as a standard, but there are two issues. Its age is one factor, the other factor that is stability of the voltage is very important. The light output is guaranteed only at that particular rated or nominal voltage. What is the utilization factor? It is the index of light reflected from a luminaire. Now, supposing we said a particular lamp has say 100-watt lamp radiating 10 lumens per watt would amount to meaning 1000 lumens of flux, but all 1000 lumens may not be usable based on the accessories that are employed along with the lamp, and this is what it gives. Typically, we said it is around 0.85 to 0.9. What is the maintenance factor of a luminaire? It is the depreciation of light output of the luminaire due to accumulation of dust and moisture. What are the advantages of using diffusing type of luminaire? They avoid glare. So, having said so much about the incandescent lamps and having addressed the various aspects of measurement, effect of importance of illumination, the way eye is affected, the next issue to be taken up is to consider the second effect, that is the electroluminescence, which is used in the artificial sources. That would be the topic of next lecture, which is titled Discharge Lamps 1, because I told you the electroluminescence is producing light radiation by a discharge in a gas or a metal vapor at high by creating a arc, and in creating this discharge we use filaments which have been studied today in incandescent lamps. Thank you.